Hello and welcome to Lesson 10, Part 1, the extension of the EPANET introduction. And in this lesson, we continue with various EPANET examples and some additional hydraulic modeling and design content. So we're going to discuss water distribution system components, in particular valves, and then look at a couple of examples. We'll discuss pumps, at least how they're incorporated in EPANET. Several examples there. And then we'll go into the concept of extended period simulation, where we have demand multipliers over time, which adjust the base demands at each node. And we'll then segue in example 9, which is a multi-loop network with extended period simulation, and finally conclude with the water quality simulation component in EPANET. This is a fairly long lesson or series of videos, so remember that you can pause them as needed if you want to work alongside, and you can always exit the video and resume them if you're directing to the YouTube content as needed. So valves are devices that control the amount and direction of fluid flow in a closed conduit system. They're made out of a variety of materials: bronze, brass, iron, steel alloy, plastic. The valves play a couple of different roles. There's stop valves or isolation valves. Their purpose is to completely shut off flow of fluid, and they're used to isolate portions of a system for repair. Examples of the types of valves that are used are globe, butterfly, gate, plug, and needle. All of these can serve as strict isolation valves. The needle valve is a special kind that's actually used to partially shut off flow. It can be used to accurately essentially change the diameter in the valve body of the flow area, giving fairly precise control of volumetric flow rate. Check valves, they're intended to permit flow in only one direction. The electrical circuit equivalent's a diode. The technologies in hydraulic systems are ball check valves, swing check, lift check, and I'm sure there's a few others. And then there's a special category of valves, remotely operated, pressure reducing, pressure relief valves. These are used to control pressures and or flow on either side of the valve by a variety of springs and diaphragms. A pressure reducing valve is functionally equivalent to the regulator in a scuba system. Here's some pictures of different valve types, globe, showing the different parts. Important component is this the actual globe valve and then the valve seat. So this thing is pushed down or up into this seat, which has a hole in it. As it's raised up, water can flow through the valve, and as it's pushed down, it cuts off the path and isolates one side from the other. Gate valve, there's a circular gate right here. Think of it as a knife being pushed into the pipe and lifted. You lift the knife to let flow occur, and you push the knife down to stop it. Butterfly valve is a disc, and the disc is rotated within the valve body. If it's in the position depicted here, the valve is fully open, and by pulling this handle, you can adjust the angle that the disc is all the way to closed. Valves in EPANET are treated as links, and they limit pressure flow at a specific point in the network. The kind of valve types that can be implemented in EPANET are check valves, shutoff valves, basically opening and closing a link, pressure reducing, pressure sustaining, and pressure breaker valve. These are documented in the documentation. Flow control valve, throttle control valve, and a general purpose valve. The general purpose valve, you as the analyst would have to provide the various valve rules directly to the software, and it's not really a scripting language, but there's ways to provide rules in the input file. The parameters that valves have as a minimum are the beginning and ending nodes. Remember, they're treated as links, the nominal diameter of the valve, and then the valve type. And then there's the initial, the setting, and then the status of the valve. Status is open and closed to start with, and then depending on the rules, if you apply them, it can change as the simulation proceeds. The output parameters, or what the valve produces, is a flow rate and a head loss. Let's look now at example 3. We're going to continue with our EPANET training. And in this example, we're going to simulate a loop system with multiple sources. We're told that the elevation of all the nodes is 50 meters, and we want to find the pressure and flow distribution. So we will escape from the presentation, go to our hopefully working copy of EPANET. Oh, it doesn't want to work anymore, does it? Of course not. Oops. I happen to know where it's located on my computer. Get EPANET up and running again. There we go. So there's my EPANET. Let me make it small for the time being. And I want to go to the class website where I have the files for exercise example 3. Now all I'm going to do is actually grab the bitmap file. So I simply want the bitmap, and I will, oh, that wasn't what I wanted to do. Well, it's here now. Let me put it onto my desktop, and then let me put it into Playhouse directory, and we'll leave it right there. So the reason for doing that is so that I can go ahead and load it from Playhouse, example 3, and there is the bitmap. If we quickly return to the presentation, we have the roughness height is 0.26 millimeters, and all nodes are at elevation 50. All right, so this is in SI units, so let's go ahead and set the defaults to an SI unit. I am going to choose liters per second, and because we're given a roughness height, we can assume Darcy-Weisbach is the preferred head loss model. Now we follow our modeling protocol. We've drawn the network. We've labeled the various items. So there's node A, B, C, D. We'll go ahead and actually prepare those labels. Node A, elevation is 50. There is no demand at node A. Node B, elevation is 50, and the demand is negative 200 liters per second, which would be 0.2 cubic meters per second. Go to node C. Its elevation is 50. No base demand. And finally node D. Elevation is 50. Base demand is 200 liters per second. All right, those have been established. Let's now go ahead and connect the pipes. as pipe P AB. It is 700 meters long, 250 millimeters in diameter, a roughness of 0.25, 26. Save it. This is pipe BC, 800 meters long, 300 millimeters in diameter, 0.26, 0.26 millimeters high. Save it. Here's pipe CD. Actually, it's pipe DC is drawn. 1,200 meters in length, 350 in diameter, and 0.26. This is pipe AD. It is 1,000 meters long, 400 millimeters in diameter, and 0.26. So our pipes are drawn, at least our network is drawn. We're going to have our two reservoirs, and I'm going to introduce them into the network with two additional pipes, and we'll make those pipes fairly short, large diameter, and very smooth. So that is, those pipes essentially provide no head loss whatsoever, and so they're basically directly connecting this 75 meters ahead to node A. We'll play the same one here, fairly short, large diameter, very smooth. Finally, we'll specify the total head of that reservoir as 70, the total head of that reservoir at 75. And we should now be ready to run the simulation. We can kill the backdrop, and that is indeed the pipeline model. Let's go ahead and get that taken care of. Okay, so the pipes are now labeled, the nodes are labeled. We're ready to run the simulation. We run it, and the flow arrows are now indicating direction. And if we want to see what the numerical values are, I've got to go hunting my browser. There it is. We can turn on the node map and look at, let's see, pressure and flow, and it's done a best job that it can on selecting a color scheme for us, and now we have produced a solution. We would expect that this 184 and the minus 15.33 should, 184 and 15.33 should add up to 200, which is the demand at node D, and 136 plus 63 should add up to 200, which is the injection at node B. We see that there is a component of flow coming from this reservoir of 121.22, and there's 121.22 leaving reservoir into reservoir 2. That completes example 3. So our next example is example 4, and this will be a more elaborate network, and we'll pick it up in a subsequent video. So that completes part 1 of Lesson 10. Thanks for your attention. Bye.